This is a video on finding particular solutions. The difference between general solutions and particular solutions is that a general solution is going to retain the constant of integration c and therefore represent a large group of functions with the same base, and then you have that additional plus c. It could be any real number. So in fact, you have infinitely many different answers. That's what a general solution is. So for example, if I were talking about general solutions for something really simple, like let's integrate x dx, we would get 1/2 x squared plus c. And that family of graphs are all related to 1/2 x squared. And you could have a +1 here, a +2, a +38, minus 4,053. So you really could put any c value in there, take the derivative, and end up with this same function x. So that makes that a general solution. What's going to happen with a particular solution is we're going to have one more piece of information, which then will allow us to find that c value. So it's a specific one answer out of those infinitely many general solution equations. So just to recap what you should already know, this side is the general solution side. So we have our function, lowercase f of x equals 7x to the fourth. We're finding the antiderivative. A couple different ways we could see this. This could be, we could take the integral of 7x to the fourth dx. And our power rule says let's raise the exponent by 1. And let's divide by that new exponent. So in this problem, that should give us 7/5 x to the fifth. And anytime we integrate with definite integrals, meaning there's no numbers on the integrand symbol, we're going to get a constant of integration c. So our general solution for 7x to the fourth, when we integrate, we get 7/5 x to the fifth plus c. And again, here we are doing the same exact process. Okay, 7x to the fourth, blah, blah, blah. And we get our same general solution. However, I've added an initial condition to the situation. This is the point x is 1, y is 3. And since we know that f of x here, capital F of x, can be used as a y, I'm going to take my point, which again you can't see here, it's 1, 3. I'm going to put my y value in. I'm going to put my x value in. And what is left but an expression or an equation where the only variable is that c. Every equation is going to be a little bit different, but we're going to solve for c using some simple algebra. Here, 1 to the fifth is 1 times 7/5 is 7/5. That's what I've got here. And now it's 3 equals 7/5 plus c. And then very simply subtract 7/5 from both sides. 3 is 15/5 minus 7/5 is 8/5. That is the c value. Okay, so really what happens is this particular piece here makes it so that I'm talking about a very specific equation, not a general equation, but a specific one. And once I find that c, I plug it in here, and it gives me my particular solution. I've got a couple other examples to show you. F of x equals the cosine of x. So we're going to find the antiderivative of f, lowercase f, if we have this given information. So this must be the point. So another way to think about this is I have x and y. It's really the point 7 pi over 4, comma, I'm just going to rearrange that, 1 minus root 2 over 2. Okay, so we're going to integrate cosine of x dx. And the antiderivative of cosine is sine, add the c. Again, f of x is equal to y, so I'm going to replace my y value here. I'll color code it for you. It's a little bit easier that way. Ooh, okay, there's my y value, here's my x value, I plug them into my equation, and then it's evaluate and solve. So the sine of 7 pi over 4, a little refresher if you don't remember your unit circle, 7 pi over 4 is right around here. It is negative because it's the sine value, and it's root 2 over 2 because it's a multiple of 45. So that's where I'm getting the negative root 2 over 2. And you're going to see why I had such a weird number in here for the y value. If I have a negative root 2 over 2 plus c here, if I add the root 2 over 2 to both sides, these will now cancel, right? And I'm left with 1. So the c value in this case is 1. Go back up to my general solution, use exactly the same thing, except now I know c is 1. So there's my particular solution for that problem. Now here's another way you might see these problems. You might see the problems given to you in the form of a dy dx, which is a differential equation. Essentially, this is saying the derivative of y with respect to x is this. Okay, let's ignore the 3, 5 here. That's our initial condition. So one thing that I like to explain to people for this type of problem is that I want to get rid of this dx. So I'm going to treat it as if it's a variable. So I'm going to multiply both sides by dx over 1, essentially canceling these dx's. And I end up with dy equals 4x cubed minus 6x squared dx. And now I'm able to, really I can put a 1 here, and I can integrate both sides. I can take the antiderivative of both sides, because now here I can take the antiderivative of 1 with respect to y. And I could take the antiderivative of all of this side with respect to x, because the variables all match up. So what ends up happening on the left side, the antiderivative of 1 in terms of y is going to give us y. And the way I like to describe that is, hey, I'm taking the antiderivative of the derivative of y. So the antiderivative of the derivative of y is simply just y. And then I use the power rule on the other side. So I'm going to say, hey, that's x to the 4th. That ends up being negative 2x cubed. And then I can't forget my constant of integration. Then I revisit the fact that I've been given this other piece of information where x is 3 and y is 5. So you can see I've plugged in my x value 3. Anywhere there's an x, there's 2 x's, so I've plugged it in twice. And I've plugged in my y, which is 5. And I have this equation. I'm going to use that equation, and I'm going to solve for c. So 3 to the 4th is 81. 3 squared is, oh, that's a mistake. Look at that. I got to fix that. So let's, well, glad I caught that. 3 cubed is 27 times 2 is 54. And we're looking at, I think that's 27. So if I subtract 27, I should get negative 22. Hopefully I didn't make a mistake there. Kind of going on the fly. And I'm going to have to correct this 58 here. That is going to be negative 22. Let's see. Yeah, that seemed right. So just go through with your antiderivative rules that you are now aware of. And then once you have your general solution, plug in your x and your y's, or whatever the variables represent. Solve for c. Rewrite your equation in terms of a very